Hi geographers, welcome to this second video about sea level change. In today's video we're going to be looking at the different landforms created by either a rise or fall in the sea level. And to start with, it's probably worth us just recapping some of the key bits of terminology associated with sea level change. So what I'd like you to do at this moment, pause the video and see if you can define those 5 key phrases on the screen. So the first one then, tectonic sea level change. This is a change in the sea level, that could be a rise or a fall, associated with the movement of tectonic plates. So perhaps following an earthquake, we might see an area rising or falling as a result of changes in the ground level. This tends to be quite sudden, as in literally a few seconds for an earthquake to happen, and it tends to be quite localized or very localized in its extent, so it's only affecting quite a localized area. Eustatic sea level change, on the other hand, this is change on a global scale, okay, and it's a change in the volume of water. That's the key thing to remember. Change in the volume of water in the world's oceans. So either a rise or a fall in the amount of water in the world's oceans. So this is a relatively slow change, and it is also a global one. All of the oceans are connected, so therefore sea levels will rise globally. Not always completely equally, because there are other factors at play, but generally speaking that is a global impact on sea level change. Isostatic change, this is a change in the height of the land relative to the sea. It's normally caused by the weight of ice sheets either being added to or lifted off of the crust. Again, this tends to be a relatively slow process, and it is a localized one. It's only going to affect the area where the ice sheet was located and the areas immediately surrounding it. Emergence is just another name for the situation where the land is rising, okay, or the sea level is falling. So it's a relative fall in the sea level. Now that idea of it being relative is important, because actually the land could rise and you would have created a relative fall in the sea level. Submergence is the opposite. It is the land sinking or subsiding, or the sea level rising. Overall, it is a relative rise in sea level. Well done if you managed to get all of those key terms summarized correctly. I'm going to move on now to have a look at some of the landforms that exist on both emergent and submergent coastlines. So emergent coastlines are evident where we can see that relative to where it is now, the sea level was higher in the past. Okay, most often this is marked by the formation of raised beaches. As their name suggests, beaches that were once at sea level but have now been raised or have risen above the level of the sea currently. These raised beaches tend to be deposits of sand and pebbles. They might be on gently sloping platforms, just like we would find a gentle slope on a beach currently. And they tend to be backed maybe by old cliff lines, what we call relict cliffs. And those cliffs contain other coastal features like caves or wave cut platforms, sometimes even arches and stacks. And in some cases, these features, these coastal features, can actually be significantly higher than the present day sea level. So in Scotland, for example, estimates put that the land has rebounded by over 100 metres since the retreat of the ice sheet that covered the north of the UK in the last glacial maximum about 16,000 years ago. So those coastal features that were at sea level are now 100 metres or so higher than the present day sea level. Just going to cut now to a classic geography clip of Mr. Alan Titchmarsh having a look at some of these features in Scotland.
There's nothing quite like an afternoon on the beach, is there? Soaking up a few rays, seagulls screeching overhead, sound of the waves lapping gently on the shore, the prospect of an ice cream, and a short walk to the beach for a paddle. But on the Scottish island of Jura, things aren't quite what they seem.
I'm most definitely on a pebbly beach, but there's something strange about the pebbles.
These rocks are certainly typical of those that are worn by water, because they're all rounded and smooth, and yet they've got lichens growing on them. Now, lichens only grow on rocks that are stationary, not on those that are washed by water. So what's going on? Well, while these rocks were clearly once pummeled by the waves, they're not anymore, because the sea is 40 metres down there.
It's hard to believe that this towering cliff was once battered by waves. This sea stack is now surrounded by grass, not water. Waves carved out this arch, but it's been left high and dry. And it's all down to ice.
Like everywhere else on Earth, Jura today floats on a layer of molten rock about a mile beneath the surface. Now, when the great ice cap formed, the weight was so great that it pushed the Earth's surface down into the molten rock. And as it melted, so the land rose up again. And the beach that was once here is now 150 feet up there and still rising.
So we had enough ice to sink an entire country.
Okay, a few photos just to illustrate some of the features that we have seen there. So you can see in this photo on the right hand side we've got an area of sediment that's been deposited. Clearly looks like a beach would do. If we were to look more closely at some of these stones, they would be a little bit more rounded and smoothed off by the process of attrition. And then we can see we've got a drop down here to where the present day beach and sea level is at the moment. So the current sea level is here. This is on the Scottish island of Jura, and a great example here on the right hand side of one of those raised beaches that we've been talking about. This beach would once have been at sea level. The sea level would have been here. As a result of isostatic rebound and the land in Scotland rising, relatively sea levels have fallen, and that has caused this raised beach to be created. Here's another example. This is actually from Greenland, and Greenland is obviously somewhere that is currently experiencing melting of its ice sheet, and therefore the land is experiencing isostatic rebound. And you can trace quite clearly actually the different levels of this beach. See all the different lines on that photo there of how that sea level has retreated and retreated over time, creating almost like a series of little raised beaches, a series of ridges. If you look in the background, you can see perhaps evidence of some of those relict cliffs, those fossil cliffs that we've been talking about as well. Some more fossil cliffs in this picture here. We can tell they're obviously not at the present day sea level because they've got grass growing in front of them, so that wouldn't happen if this area was washed over by the sea. The rocks in the foreground on this wave cut platform, we can see that they've got lichens and other vegetation growing all over them. You've got some people in the background there to give you an idea of the sort of scale of these cliffs. So these are tall features, large caves and wave cut platforms and wave cut notches. And obviously they are no longer at sea level. As a result of a relative fall in the level of the sea, these features are now above the level of the present day sea level. Same with this little stack that we can see here. Same with this archway here. Imagine taking Durdle Door and actually lifting it 20, 30, 50 metres above sea level as a result of that isostatic rebound. So definitely no waves washing underneath that arch at the moment, but that would have been happening in the past. Here's a little diagram just sort of illustrating the layout of these sorts of features. So the present day sea level, the present day beach, and then what is presently the cliff line here. And then perhaps that vegetated wave cut platform with those sort of fossil caves and cliffs and wave cut notches behind. It's worth probably reminding ourselves that these features have just been formed by the same coastal processes that create caves and beaches and arches and stacks and whatever else at the present day. There's nothing different that's formed these features. The only thing that's happened is they used to be at sea level and they're not anymore. So in the case of the island of Jura in Scotland, a great example to use, as a result of isostatic rebound, those features have been lifted above the present day sea level, and that vegetation's grown on it, which has maybe hidden some of the features like the beach sediment and maybe made it less obvious that actually it's a coastal feature. So they are the main emergent features that we find. Erosional or depositional landforms like beaches that have been lifted above the present day sea level. We're now going to cut back to Mr. Alan Titchmarsh and have a look at the other end of this scale and have a look at submergent landforms. Let's have a look at what's going on here.
Yes, unlikely as it may seem, that place is on board a fishing boat. Somewhere out here is more evidence of Britain's past.
This is the North Sea, about 80 miles off the British coast, and I'm on a fishing trip with a difference, hoping to catch something a bit out the ordinary.
But what can a net load of starfish and crabs tell us about conditions south of the vast ice sheet? Well, nothing. But if you're lucky, they're not the only things you can catch. I'm here with Dick Mole, a specialist not in fish and crabs, but fossils. Although, even with his help, finding what we're looking for is harder than expected.
That's wood, isn't it? Not up there. That's wood. Tree. Gardening, you see. Wood. 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 What's that there, is it? Wood. Wood. A bit of rib? No wood.
But with the next catch, we struck lucky. Now, what does this look like to you? A tusk?
Oh, wow.
Exactly. This trawler isn't after fish or crabs, it's fishing for mammoths.
Yeah, right. A good specimen as well. Excellent.
Amazing.
Heavy.
Very heavy. Ivory.
This is pure ivory, but fossilized.
From the bottom of our very own North Sea, we just pulled up the tusk of a prehistoric mammoth. Amazing as this was for me, out here, it's an everyday occurrence. And it wasn't just tusks.
Size of that. Don't tell me this is a back leg of a mammoth. Or is it just a bigger mammoth's front leg?
This is front leg as well.
Yeah.
Upper part.
So have we got two pieces of one leg?
Maybe one animal.
Yeah. These were big animals. It takes some dog to get its jaws around this.
So far, the remains of 50,000 mammoths have been found at the bottom of the North Sea. Fishermen first discovered the bones over 100 years ago. They gave them to the local doctor for identification, and he announced that finally this was evidence of Noah's flood. And while opinions on Noah may be divided, they were right about the flood. During the Ice Age, so much water was locked up in glaciers and ice sheets that sea levels around the world were much lower than today. The North Sea didn't exist, and the Thames was a mere tributary of the ancient German Rhine, which ran down the middle of where the English Channel is today.
Okay, so as the name suggests, submergent coastlines are caused or formed by the rise of the sea level, submerging or flooding low-lying land masses. So areas that were once quite close to sea level get flooded as the sea level rises. In particular, this has quite a profound effect on existing river valleys and existing glacial valleys, and as those valleys get flooded, they almost become new landforms in their own right that we're going to have a little look through now at each of these sorts of examples. First one that we can start by thinking about are rias. So rias are flooded river valleys. When a river valley gets flooded and submerged by a rise in the sea level, or indeed a fall in the level of the land, remember isostatic change can work in both directions, so if the land was to subside, the same thing would happen. But as a result of that submergence, we flood an existing river valley. So these features, rias, they share the same kind of shape as a normal river valley. They share the same long and cross profiles. So for example, if we think about the long profile of a river, if we went from B here at the sort of upstream end of the river down to A at the mouth of the river, we would notice that initially that long profile drops quite steeply, and then it starts to flatten out as we get towards the sea. That's what we expect to find with a river's long profile. Same with the cross profile. If we were to think about going from X to Y here across the river valley, then we'd notice that it tends to be quite wide, quite gently sloping, okay, quite a broad valley because we're quite near the sea. Further up the river's course, we might expect the river valley to be a little bit more V-shaped, but down towards the mouth we'd expect a broader valley. So what that means is rias tend to be very wide. So we notice them when we look on maps of the coastline as being rivers that look unusually wide. A great example of that are the estuaries in and around Dartmouth and Kingsbridge on the south coast in Devon. We're going to cut and have a look at those on Google Earth in a minute, but more locally to us in Dorset, Poole Harbour is actually a great example of a RIA as well. So Poole Harbour is obviously the mouth of a few rivers, particularly the River Frome coming down here through Wareham, and those rivers originally would have flown out into the sea, okay, at this point. But sea levels have risen and this area has been flooded by a rise in the sea level. So places like Brownsea Island, that you might be familiar with, a really obvious feature in the middle of Poole Harbour. Brownsea Island didn't used to be an island at all, it just used to be a hill, and there would have just been land around the bottom of it, and as sea levels have risen they flooded the area around the bottom of the hill, now actually cutting that area off as an island. Poole Harbour is actually only on average about 45 centimetres deep. The water depth is really, really shallow. There's a deeper part which they keep open for kind of ships and boats and things sailing in and out of it, but most of Poole Harbour is actually very, very shallow, and it's a great example of a RIA. Going to look at these on Google Earth in a second, but some photos here showing the Dart estuary of the River Dart in Dartmouth. So Dartmouth is here on this map. The photo and the map are opposite way round. So in the photo, Dartmouth is actually down here in the distance, and we can see Dartmouth on the map here. Okay, the river is flowing this way towards the sea. Now, when you look at that map of the Dartmouth estuary, and we'll be able to see it a little bit more clearly in a minute, you get a sense of just how wide the river is, particularly even some of the tributaries flowing down into it, how much wider that river is than some of the surrounding rivers. If we look particularly at this area up here, around the area of Dittisham, you can see how wide that river is, and that's because it has been flooded and submerged. The water level there is much deeper than it would be normally as a result of this rise in the sea level. That's why RIAs tend to make very good ports. We often find them in places like Portsmouth, Plymouth, Dartmouth, along the south coast of England, where naturally these river mouths, these estuaries, are much deeper than they would normally be because they've been flooded by a rise in sea level. Let's have a little look now at this estuary on Google Earth. Okay, so we're going to have a look now. We're going to zoom in and have a look at the south coast of the UK, have a look at the south coast of Devon, and we're going to look particularly at the estuaries in and around Dartmouth and Kingsbridge. So here's that image we saw earlier, the river in Dartmouth, the River Dart, flowing down this way, meeting the sea at Dartmouth, and you can see just how wide this river valley is, and get a sense of also the fact that that area has been flooded by a rise in the sea level. If we were to actually measure how wide the river is, we'll do this in metres across from one side to the other. At this point it's 1,445 metres, or 1.45 kilometres across. That's really, really wide for actually what is essentially quite a small river. The River Dart is not a massive river by any standards. Same thing is evident on this coast a little bit further to the west. This is the estuary in and around Kingsbridge and Salcombe, and again you can get a sense of how much wider that river mouth and that river estuary is, particularly when you go upstream. Here you can imagine at high tide this whole area would be covered in water as well, and just how much wider those estuaries and river mouths are than some of the other rivers nearby. Look at this one here, for example, where the river has formed more recently, since the end of the last ice age, and this area has not been subjected to that rise in sea level since. So some great examples there along the south coast of the UK. Moving a little bit further afield, another similar feature to RIAs are what we call Dalmatian coastlines, and the best example of this is actually what is known as the Dalmatian coastline, which runs down the coast of Croatia. What we have here is the situation where rather than the rivers flowing down to the sea perpendicular to it, so for example we might imagine that most rivers would flow this way sort of down to the sea and meet the sea that way, and then when the sea level rises we might flood the lower part of that river. Dalmatian coastlines work in a slightly different way. Here, instead of the rivers running perpendicular to the sea, the rivers would have been running parallel to it. So you might have had one river flowing down here, another tributary of that river flowing down here, maybe another one flowing down in this direction. And as a result of the rise in sea level, those river valleys have been flooded and created this sort of string of islands that run parallel to the coastline, and it's just that the higher ground in between those river valleys has been left behind and the valley either side of them has been flooded. Just in the same way that Brownsea Island used to be a hill and is now an island, the same thing has happened here, but it's happened all the way along that river's course, leaving these islands parallel to the coastline, and they formed as a result of that submergence of those river valleys. Final submergent landform to have a look at are fjords. Now fjords are formed when a rise in the sea level submerges a glacial valley. Now glacial valleys have a very different shape to river valleys. Normally we would expect the cross profile of a river valley to be quite broad. If we remember back to that diagram we looked at of a Rias, we tended to find that they were sort of quite broad, this sort of shape to them, whereas a fjord has very much a U shape to it, and that's because when glaciers carve out a valley, they carve out one with very, very steep sides and a relatively flat bottom to it, so they have that classic U shape to them. This is why we call them a glacial trough. What happens then as a result of the rise in sea level is that valley, after the glaciers melted, gets flooded with water, and then you have these very long, very straight, very deep valleys with very, very steep sides. It's worth us understanding a little bit more about their shape as well. The reason that glacial valleys tend to be a bit straighter, this one's got a little bit of a curve to it, but it's not really meandering around like a river might do. The reason that happens is because a glacier just bulldozes the rock out of the way. Normally rivers don't really have the power to do that, so they have to flow around areas of harder rock. A glacier doesn't have to worry about that. It's so powerful that it just smashes through anything that's in its path. So that's why fjords tend to be quite straight. The other unusual feature about them is that the mouth of those fjords, where they meet the sea, tends to be a little bit shallower than further inland. You can see here that if we imagine we are going towards point A, following this line down here, okay, or imagine that the same would be true if we were coming to this point here, we can see that the fjord actually gets a little bit shallower as it gets towards its mouth, and that is because of the unusual way that glaciers erode the landscape around them. When a glacier is flowing down its valley and meeting the ocean, it doesn't flow across the surface in a straight line. It actually flows with a bit of a rotational movement, a bit of a curved, almost like a scooping action. So it's actually able to scoop out this part of the valley, but it doesn't have the power to scoop out this part. And very often lots of material gets deposited here at the point where the glacier meets the sea. So that explains why fjords get a little bit shallower as you get towards the sea. That's a rather unusual feature of them. Best example of places where you can find these sorts of features are on the west coast of Norway, for example. We're going to have a look at some photos of these features in just a second, but it's worth perhaps just outlining that change and that difference between a river valley and a glacial valley. So What we would find normally is with a river valley, you'd have quite a narrow valley, and it would be quite V-shaped like we can see here, and it wouldn't be that deep and it wouldn't be very wide. And perhaps during an ice age or during a glacial period, a glacier might develop in that region. Glacier is much larger than a river, and it's gouging out that classic U shape. It's bulldozing away anything in its path, and eventually when it melts, you're left behind with that classic U shape to the valley. Don't worry about all these other labels on this diagram. We're not learning about these glacial features today, but I just wanted to show you that as a good example of how a valley can change shape from that narrow V-shaped river valley to that massive U-shaped, straight, steep-sided glacial valley. So here's some examples from the west coast of Norway. Hardanger Fjord is a really good example to use. You can see how long and straight that fjord is. Obviously there were some smaller glaciers kind of feeding into it here. That's what's created these little tributaries off to the side. And when you look at it in this photo, when you look at that cruise ship, to give you an idea of scale, you can see what I mean about the size of these features. You can see the waterfall on the side there, giving you an idea about the steepness of the sides of those valleys. And again, you can get a sense of, even though there's this little bend in the fjord here, they are relatively straight features, unlike Rias, which maybe tend to be a little bit more meandering because rivers tend to meander through the landscape, whereas glaciers don't. So in summary then, main difference between emergent and submergent coastlines. Emergent coastlines, they're caused by a relative fall in the sea level. Remember, that could often be as a result of the land rising. It takes those coastal features like caves, arches, stacks, beaches, and it raises them above the present day sea level. Great examples of that, Scottish islands like the Isle of Jura. Submergent coastlines, on the other hand, they are caused by a relative rise in the sea level. What that does is it floods coastal areas. It basically drowns any existing river or glacial valleys. Particularly along the south coast of the UK, we find Rias, we find Dalmatian coastlines where those rivers used to run parallel to the sea, in places like the Dalmatian coastline in Croatia, and fjords in Norway as a result of those glacial valleys being flooded.